Today we are going to talk about partial orders. Okay. Many students come across this partial order when they want to use Zahn's lemma. And the teachers are very impatient. They quickly do it within few minutes, then immediately enunciate Zahn's lemma and try to apply. So whatever I have seen in my experience last 30 years is students are very, very uncomfortable with this notion. Okay, but believe me, it's very easy. You just have to spend a little time on the basics. After that, it's very easy. We are going to prove that. Okay, let's get started. Yeah. So, oh, there is a mistake. Let me correct. Otherwise, my dear friend Baba may be unhappy. I think my everything is as a foundation course. Yeah, see, there are some stupid mistakes. Yeah, this is what happens if you slacken for a while. Okay, very good. Let's get. So, what is a partial order? So, let us look at quickly. So, I hope that all of you know something about what is meant by a set, etc. Oh, what is this? Something is wrong. Yeah. So let X be a set. Okay. A relation which you denote by this. Okay. Remember, a relation is a subset of X cross X. This is a subset. Call it a set R. This is a subset. Then what does it mean? When I say X is related to Y, if the ordered pair XY is in R, of course, XY are in X. Okay, this is what is meant by relation, but generally we will use only this symbol because much easy, right? So a relation is said to be reflexive if X is related to X. What does that mean? Yeah, that means X must be in R for every X in X. That means if you think of X as like this, X cross X, this diagonal X cross X, this must be there. This must be contained in your relation R, right? Because these are the points X cross X. You understand that? Okay. And second, it's supposed to be antisymmetric if X is related to Y, and if you say Y is also related to X, of course X and Y are only in X, then I should say X must be equal to Y. Okay, just wait for a minute. We will give very easy and good examples. Okay, just 1 second. And the third, it's supposed to be transitive. So why it is called antisymmetric? What is meant by symmetric? If X is related to Y, then Y must also be related to X. Then you call it symmetric. Antisymmetric meaning if you say X is related to Y and Y is also related to X, then I should conclude X must be equal to Y. Right? Okay. What is meant by transitive? So again, in terms of relation, how does it matter? What does it mean? If XY belong to Y and YX belong to R, this should imply then X equal to Y. Right? So this is your XY and you say this is your YX. Okay. If both are there, okay, and just look at that Y high, think of this high coordinate. Okay. So this is X comma Y and this is Y comma X. Okay, if both are there, that means they are one and the same. That means it must be the point here. Okay, transitive means if X is related to Y and Y is related to Z, this should imply X is related to Z. Okay, notice that it's that order matters. Okay, this means XY is in R and YZ is in R. This implies x that is in R. Okay. So any relation R, okay, which satisfy 1, 2, and 3, this is known as partial order on the set X. Okay. Let us give, there is one and only one most important example if you want to understand partial order. If you keep that in mind, you will see any kind of more abstract partial orders also you can understand much better. What is that example? Very simple. Start with the set, okay, A, maybe call it S, S is a set. Okay, assume it's not empty. Then let X equal to the power set of S. That is set of all subsets A of S. Okay, A is a subset of S. Okay, then given any two elements A and B in X, that is, if I say X, Y in X, what are X and Y? They must be subsets of S. So I will call them as capital A, capital B. Okay, then I say A is related to. So one also use when it's a partial order, it's a very general thing to use this relation, less than or equal to relation. So in, if a, this is a partial order on X, then I say instead of writing this, it's very common to write X is less than or equal to Y notation. You will see why in a minute. Okay, so this is the first example. Let us do this first. So if A and B are there, then I say A is less than or equal to B. I am defining a partial order if and only if A is a subset of B. Okay. Now what is that I have to check? I have to check whether it satisfies all the three properties. What is the first property? Reflexivity. What does that mean? X must be related to X itself. That means A must be less than or equal to A. Is that true? Of course true, because A is a subset of A. Yeah. So one is true. And next is, if X is less than or equal to Y and Y is less than or equal to X, then you want to say X is equal to Y. Is that true? What does that mean here? If A is less than or equal to B and B is less than or equal to A, what does it mean? A is a subset of B and B is a subset of A. That means A equal to B. As such, they are equal. So 2 is also true. And the third is very easy, transitivity. What does transitivity says? If X is less than or equal to Y and Y is less than or equal to Z, then X must be less than or equal to Z. That means if A is less than or equal to B and B is less than or equal to C, then I want to know whether A is less than or equal to C. That's correct, because A is less than or equal to B is same as saying A is a subset of B. And B is less than or equal to C is same as saying B is a subset of C. Therefore, A is a subset of C. Right? Therefore, 3 is also true. You understand that? Okay, believe me, okay, this is the most important example you should know and you should learn about partial order. Whenever you are confused about partial order, come back to this example and understand. Okay, right. Okay, the standard example is what I'm going to give next. Okay, suppose I have a real number system, that is my X. Then I say X is less than or equal to Y, that is X is related to Y, that is X less than or equal to Y in the standard sense of less than or equal to, that is either X equal to Y or X is strictly less than Y, where this is the order relation among real numbers. You understand that? Okay, so that is the reason why we denote this less than or equal to symbol. So if to not to get confused at the for the time being, let us look at this. Okay, X is related to Y if and only if X is less than or equal to Y, whereas this is the as real numbers, the usual order relation in R. Okay, now what are the things I have to know? Whether it is reflexive, right? So that is whether X is related to X. When does it happen? If only if X is less than or equal to X. Is that true? What is it meant by X is less than or equal to X? That means X equal to X or X is less than X. Okay. When is this statement true? If one of the statement, either this statement is true or this statement is true, right? Therefore, X is less than or equal to X is, that means X equal to X or X is less than X. This is not true, but this is true. Therefore, this statement is true. You understand that? Therefore, reflexivity is true. Next is Antisymmetric. Antisymmetric, what does it say? If x is related to y and y is related to x, then x must be y. Is that true? Yeah. But what is x is related to y means? That is x is less than or equal to y. What is y is related to x mean? That means y is less than or equal to x. Then we know that means x equal to y, right? Therefore, antisymmetric is also true. And next is transitivity. Okay. What does that mean? If x is related to y and y is related to z, then I want to say x is related to z. That's of course is obvious, right? Why? X is related to y means x is less than or equal to y. This means y is less than or equal to z. Therefore, this means x is less than or equal to z. But that is same as saying x is related to z. You understand? Because of this only, this relation partial order, whenever partial order is there, we usually use this symbol less than or equal to symbol. Okay. So one would say this may be that correct symbol to say, but unfortunately, this is a totally ordered set also. So this is not a very good example for partial order. I will come to that in a minute. Okay, don't worry. Okay, but the next most important example. So let me again repeat. I will. Okay, let me finish. So among in natural numbers. Okay, now give me two a and b. I say a is related to b. So notice that I want to say A is less than or equal to B, but natural numbers is subset of R. Therefore, you may think this less than or equal to is the standard order relation. Something like 4 is less than or equal to 5 makes sense. That's not what we want. So I say A is related to B if and only if A divides B. You understand that? Therefore, 4 is not related to 5 because 4 does not divide 5. You understand that? Yeah? Okay. Is that clear to all? This is our relation. Now, what are the things I have to prove? Reflexivity. That is clear. A is related to A because A divides A. Notice that, yeah, this is a natural number, therefore there is no question of 0 here. And next is antisymmetric. What does that mean? If A is related to B and B is related to A, I want to know whether A is related to B. Alright? But this means A divides B and this means B divides A, so I have to say A equal to B. Okay? All of you will be ready to accept this because you know that this implies A equal to B. But let's quickly go through a proof because beginning students may not know. MSc students must know. If A is divides B, that means B must be some R times A. And B divides A, that means A must be some S times B. You understand that? So substitute here, that is RS times B. In place of A, you have substitute. This means B into 1 minus RS is 0. You understand that? That means what? Now remember, B is in N, therefore this is non-zero, therefore this means 1 minus RS is 0. That means RS must be equal to 1. Where are R and S? R and S are in natural numbers. So the product of these two natural numbers is 1. When does it happen? If and only if R equal to S equal to 1. That means B equal to A. You understand this? Okay, right. You follow this? Okay, let me repeat this. If at all you want me to say what are the most important examples of partial order, I would say the first example of set theoretic containment and the third example of divisibility in natural numbers. These are the two most important examples. Okay, whenever you are in trouble with the partial order, come back to those examples, understand them in in this context. We will see some examples soon. Okay, now why it is called partial order? We say an order, okay, a partial order is a total order if given any two for every x and y in S, either x is related to y or y is related to x. That means in terms of relation, either xy must be in R or the ordered per yx must be in R. You understand that? That means one usually says, given any two elements, you can compare them. Okay. When I say x is related to y, I simply say I can compare x and y, and I say x is less than equal to y. Okay. So one says it's a total order. If given any two arbitrary elements in x, I can compare them. That means either x is less than equal to y or y is less than equal to x. Okay. In terms of partial order, I'm saying less than equal to or x is related to y or y is related to x in terms of relation. Do you understand this? Okay. Now you can see, now the example 2 is a total order because given any two distinct real numbers, like law of trichotomy says either x is strictly less than y or y is strictly less than x. You understand that? Yeah. Therefore, x less than equal to y is true or y is less than equal to x is always true. You follow that? Therefore, this is 2 is a totally ordered set. So, if the order is total order, then we say this is a totally ordered set. If this is a total order, or we say it's a partially ordered set if this is a partial order. Notice that any totally ordered set is also partially ordered. Okay. Whereas let's look at example 1 and 3. Now you see our problem. See, example 1 and 3 are you okay? 1. Suppose x has at least two elements. Okay, sorry, yes, has at least two elements. Then x will to this, okay, with respect to the standard relation of inclusion or containment, this is a partial order but not a total order. Why? Because look at, suppose A and B are two elements in S, then look at singleton this set as A and B as singleton B, and A and B are distinct elements. Since S has at least two elements, look at this. Then can I say A is less than or equal to B or B is less than or equal to A? One of them must be true. I can't say that. You understand that? So this is an example of a partially ordered set which is not totally ordered. That is why I like this example, because whenever you want to say partial order, most often it may not be totally ordered. So we have to work. You follow this? And the example 3 is also okay. With this, okay, here I don't want to use less than equal to notation because it may cause confusion, because there is a natural order of natural numbers. So I don't want to use that. So when do I say A is related to B? If only if A divides B, right? Now you can see if I take 4 and 5 or 2 and 3, okay, 2 is not related to 3 and 3 is also not related to 2. Why? Because 2 does not divide 3 and 3 does not divide 2. You follow that? Yeah. Therefore, this is again an example of a partially ordered set and not totally ordered. So this is always this is partially ordered but never totally ordered. Not at all totally ordered. Here I have to put a restriction. The S must have at least two elements. Okay, because if it has one element, then what is P of X? It consists of empty set or the singleton. So you can always find a relation between them. Okay, think about, pause, review, proceed. Okay, right. So as I said, I will concentrate only on examples 1 and 3. And when I do example 1, I will always assume the set S has at least more than two elements, so that you don't look at some trivial cases. Okay, right. Let us look at we need few more concepts before we come to our goal. What are the concepts? First thing is, okay, suppose X is a partially ordered set. One usually calls it in discrete mass, one calls it poset. It is partially ordered set. Okay, and suppose A is a subset of X, right? Then what I want to call is an upper bound. I say an element X naught in X is an upper bound for A, right? It's a, think of real number system. If A is a subset of real numbers, when do I say X naught a real number is an upper bound? It's exactly the same definition. That is, for every A in A, okay, A must be less than or equal to X naught. This must be true. Then I call X naught as an upper bound. Okay. It looks obvious, it's a very correct definition, but you should pay attention. Notice that this is a partially ordered set. So we are making some very demanding thing. Given any A in A and an X naught, okay, since it's partially ordered, I may not know whether A is less than or equal to X naught or X naught is less to A, because none of them may be true. You understand? But what we want, when I want to say X naught is an upper bound, I have to insist given any A in capital A, and I can A and X naught can be compared. That is either A is related to X naught or X naught related to A, but not, one of them must happen. Not only one of them must happen, I'm claiming only this must happen. That is A must be less than or equal to X naught. Do you understand this? Yeah? Let us look at an example just to make sure that you know. Okay? Right? Let us look at the set S. Okay? For simplicity, let me assume X is equal to, let us say, 1, 2, 3. Okay, and let's look at x to cube power set of S. Right. Now let me look at the set A equal to singleton 1 and singleton 2. Right. Then I have an upper bound. Let it take B equal to 1, 2. Then you can see B is an upper bound for the set A, because singleton 1 is a subset of B and singleton 2 is also subset of B. You understand that? Or more generally, if I take X itself, namely, sorry, S itself, then yeah, okay, every element of A is less than or equal to every, yes, you understand that? Don't get confused. Yeah, 1, I want to say is less than or equal to yes. This is same as saying singleton 1 is a subset of S. Is this correct? Similarly, singleton 2, you understand? Yeah. More generally, if you want slightly non-trivial example, let us look at another A. Okay, 1 comma 2 and 1 comma 3 and 2 comma 3. Okay, these are all two element subsets of this. Okay, if you want now make S equal to 4. 1, 2, 3, 4. Right. Now I want an upper bound for this. So how many upper bounds I can do? So I can take my B to, okay, the set B to be 1, 2, 3. You can see 1 comma 2 is a subset of B, 1 comma 3 is a subset of B. Therefore, take any element, okay, here, X here or A here, and this is my X naught. A is less than or equal to X naught. Do you understand this? Or I could have taken this to be 1, 2, 3, 4 also. You understand? Yeah? Right. So this is an upper bound. But let's look at slightly non-trivial example in terms of number theory. Right. Now let my set X, it consists of all numbers of the form 2, 3, 2 squared, 2 times 3, 3 squared, and let me say 2. Okay, this is good enough, I think. Yeah. Okay. And what is the partial order? This is a subset of natural numbers, right? So I use the third example, example 3 order, right? Therefore, what do I know? That's what I want to look at. Yeah. Okay. Maybe I will also say 2 squared, 3 squared. Okay. Right. Now let us look at the subset A equal to 2, 2 squared and 2 times 3 and 2, 3 squared. This is 2 times 3, right? Now I have the element A, which is 2, 3 and 2 times 3. Do I have an upper bound for this? Notice that there is an upper bound here itself, namely 2 times 3. 2 times 3 is an upper bound for the set A because 2 divides 2 times 3, 3 divides 2 times 3 and 2 times 3 divides 2 times 3, right? Therefore, this is an upper bound for A. Yeah. So here the upper bound is already an element of this. Whereas here the upper bound is not an element of the set A. Do you understand these two difference? Here the upper bound, take any upper bound, okay? Yeah. Take any B which is an upper bound. That means 1, 2 must be a subset of that. That means B must contain 1 and 2. 1, 3 must be a subset of B. That means 1 and 3 must be in B. Therefore 1, 2, 3 are in B. You understand? 2, 3 must be contain subset of 3. That means 2 and 3 must be there. Therefore, any subset which is an upper bound for any of these things must contain 1, 2 and 3. You understand? Therefore, so this is in some sense the smallest upper bound. This upper bound is not an element of the set A. Whereas here, this is an element of the set A. Okay, therefore, what do you understand? Upper bound need not be an element of the set. You see that? That's why we say x naught is an upper bound for A, but x naught need not be an element of A. Do you understand? So pause, review, proceed. Okay, right. So now the next we want to look at another definition. I say A is a subset of X is a partially ordered set. Okay, I say A in A is a maximum of A if for all X in A, I have X is less than or equal to A. Do you understand that? Right? So what is important here? That A must be an element of A. This is very crucial. Then only I use the word it's a maximum. So now what is the relation between maximum and upper bound we have seen? Notice that A of course is an upper bound of A and A must also be an element of A. You see that? We already saw an upper bound need not be an element of the set. So if an upper bound of a set A belongs to or is an element of the set, then it is a maximum. Notice that I am using the word A maximum. But it's because we are in a partially ordered set, we will show that it is unique. What does that mean? If B in A is also a maximum of A, then A must be B. Why? Since A is a maximum and in place of X, I can take B. Therefore, B must be less than or equal to A. And since B is a maximum, what does it mean? For all X in A, I should have X is less than or equal to B. In particular, take X equal to A must be less than or equal to B. So I have A is less than or equal to B and B is less than or equal to A. Therefore, by antisymmetry, A must be equal to B. You understand that? Therefore, if at all a maximum exists, it is unique. Okay. Please follow everything. So what did we define? We define an upper bound of a subset of a partially ordered set. What did we observe? The upper bound may or may not be an element of the given set. Next, what did we say? We define what is meant to be a maximum. What is a maximum? Maximum is nothing other than upper bound, which is also an element of the set. That's it. Very easy. You understand? Very good. Okay. I want you to understand this because many students have a problem with the another notion associated with partially ordered. They get confused with these two notions. That's why I want you to understand this. Okay, I'll come to that. Okay, bear with me. Okay, right. The next thing we want to say is, suppose A is a subset of a partial ordered set, and I say A is totally ordered. Notice that if A is a partial ordered set, then this A itself I can call it as a partially ordered set. If X is a partially ordered set, I can consider A as a partially ordered set with respect to the same relation on X. Suppose this is a partially ordered set, then restrict this relation to A. That means what? If you give me A and B in A, okay, I define A is related to B if this holds in X. Are you following? Remember, your relation is R on X cross X, right? So if you give me two elements A and B, in A, I want to say A is related to B if AB belong to R. So that means any partial order on X induces a partial order on A. It defines a relation on A, but you have to check it is partially ordered. That is very easy because you give me A in A, then A belong to R. That means A is related to A. And similarly, if A, B are in A, and if you say A, B is in R and B, A is in R, then I know A equal to B. You understand? Please pay attention. Okay. Given any relation on X, it induces a relation on a subset. That is very easy. Okay. Next, what I want to say is if the relation on X is a partial ordered set, then the relation on A is also partially ordered, partial order. That's what you. That's very easy. But I okay. Pause. These are all very easy concepts because people don't spend time, so they get confused. Okay, go through that. Okay. Now the important notion comes. I say yes, A in X is a totally ordered subset. Or nowadays people call it a chain in X. It's a totally ordered subset of X or a chain in X if this induced partial order with respect that this is a totally ordered set. Okay. Again, since this is the first time you are looking at such things, it's better to go look at some examples. All right. Let us look at very simple example to make you understand. Suppose I take x equal to, let us say 0, 1. Sorry, s equal to 0, 1. And my x equal to partial ordered power set of s. Then what is the partial order? Standard inclusion. That is, given two sets A and B, subset of 0, 1, then I say A is less than or equal to B if and only if A is contained in B. Okay. Now I want a totally ordered subset. See, this is a partial order, right? For example, if I take 0 half and let us say 1/4, 3/4, okay. So this is my A and this is my B, then A is not less than or equal to B and B is not less than or equal to A. You understand? So this is a partial ordered set. But can I think of it totally ordered set? Yes. Let us look at for each real number t in 0, 1. Okay, let me look at the set AT equal to 0 to t. Okay. You understand the interval 0 to t. So therefore, this is my 0, this is my 1, t. So my A, this is AT. Now this is a, now look at the collection. Okay, this is my collection. AT. This is my subset, what I call A subset of X. Okay, this subset is the collection of all subsets AT. This is a subset of X, which is P of S. You understand? Now I claim this is a totally ordered subset. Is that clear to you? Yes. Why? because you give me S and T, right? If S is less than or equal to T, then AS is a subset of AT. You understand that? Since S and T are real numbers in 0, 1, because where is T? T is in 0, 1, right? So if you give me two real numbers, two elements here in this, call it AS and AT. Now S and T are real numbers in 0, 1. Therefore, either S is less than or equal to T or T is less than or equal to S. Accordingly, AS is a subset of AT or AT is a subset of AS. You understand that? Therefore, this is a chain. Okay. Which is, what does it mean? That is, any two elements are you can compare. One is less than or equal to, given any two elements in this collection, one is a subset of the other. One of them must be a subset of the other. Is that clear? And notice that how many elements are in this subset? Uncountably many. As many elements as there are real numbers in 0, 1. Because many times students have problem, even MSc students, whenever there is a totally ordered subset or a chain, they think it is a countable collection. It need not be. Here it is uncountable collection. Do you understand this? Okay. Spend some time. Okay. Let us look at another example. So now this time we will take x to be, let us say, some 2 power r into 3 power s, where 1 is less than equal to r plus s is less than equal to, let us say, 2. I want to make my life simple, so I just made it 2. Okay, maybe, okay, make it 3 then. Okay, yeah, make it 3. Then what are the elements here? See, r and s, see, none of them can be less than 1, right? Okay, let us make it r must be greater than equal to 1 and s must also be greater than equal to 1. Maybe I should allow them to be 0 also. R plus s, yeah, r is greater than equal to 0, s is greater than equal to 0, but r plus s must be less than. Okay, let us put that condition. R is greater than equal to 0, s is greater than 0, but r plus s must lie between 1 and 3. That is, r equal to 0, s equal to 0 is not allowed. You understand this? Both cannot be 0. One of them can be 0, but not both, because the sum must be at least 1. Therefore, what are the elements? So, r can be 1, s can be 0, or r can be 0, s can be 1, and then this is r plus s equal to 1, then r plus s equal to 2. What are the possibilities? 2, 0, 0, 2, 1, 1. Therefore, it is 2 squared, 2 times 3, and 3 squared. And next will be r plus s equal to 3. Therefore, 3, 0, 2, 1, 1, 2, then 0, 3. I hope these are the only ones. Yeah. Therefore, this is going to be 2 cubed, 2 squared 3, 2, 3 squared, and 3 cubed. You understand this? Sure? I hope I did not miss out any element. In case I did, okay, bear with me. It's all right. You have to understand what is happening. That's more important for me, right? Okay. Now let us look at the subset A, right? Let me look at the subset A, which consists of 2, 2 times 3, and 2 squared 3, okay, and 2, 3 squared. Now I want to know whether this is a totally ordered set. Notice that this is not a, this partially ordered. The set X is partially ordered, but not totally ordered. Yeah, partially ordered for the obvious reason. 2 does not divide 3, 3 does not divide 2. Therefore, 2 is not less than equal to 3, 3 is not less than equal to 2. Not related to, right? Is this partially ordered? Take any two elements. You have to say one divides the other. That's very clear. Take, for example, 2, 3, and 2. So this divides. 2 into this divides. Therefore, this is partially ordered. This is a totally ordered set. You follow that? And another thing, this call it A1, call A2. This can be, for example, 2 times 3, 2 squared times 3, and 2 times 2 squared into 3, that's it. And 2, that's it. So I can give up to 3, right? Therefore, I could have done 2, 2, 1, 0, 2, and none of them could be 0, right? Yeah, 0, 0, right, right. Okay, this is it. Yeah, that's it. Because I cannot have any more element, right? If I want to have anything else, this must be divided. That means I should have 2 into, suppose I have 2 into 3 squared. I can't have it here. Why? This 2 times 3 divides 2 times 3 squared, but 2 squared 3 does not divide this, right? So only this is a totally ordered subset. Are you following? Hmm? You bear with this kind of example, try understand better, spend some time. So what did we talk about? We talked about totally ordered subset. Okay. Now let us look at in this example. Let us look at this is a very good example. The last example which I did is a very good example. Let us try to understand. Okay. Before that, let us look at an example. Okay, a definition. Now X be a partially ordered set. Okay. I call an element X naught in X is a maximal element, not maximum, maximal element of X. Okay. I want to define what is meant by a maximal element of X. Remember, when do I say an element, let us say A in X is a maximum if for all X in X, X must be less than or equal to A. You understand? When I say X naught is a maximal element, okay, what does that mean? That means if you tell me, okay, if you tell me X in X is such that X is greater than or equal to X naught, then I want to claim, then I want to say, I can conclude X must be equal to X naught. Okay. Now you may think both are the same. They are not. Okay. I will give a very real life example. Okay. What is the difference between confidence and arrogance? Arrogance is, okay, something like everybody is below me. Okay. That is, give me any element, I am X naught. Okay. That's I am maximum. That means give me anybody that X is below me. X is less than or equal to X naught. Okay. Right. But my self-esteem person, a self-confidence person says, if you tell me, okay, no, I'm claiming nobody is above me. You see that? I'm claiming nobody is above me. That is, I do not accept anybody is better than me. That's it. But I am not claiming everybody is beneath me, below me. Okay, that is self-confident person will say, okay, I can do it. Arrogant fellow will say, only I can do it. Nobody else can do it. Okay. Yeah, I'm just giving some kind of idea to think about. Okay. You follow that? Maximal element and maximum are different. I am going to give very concrete example, and with that we will stop. We will take it up in the next lecture. Okay. So what is a maximal element? So X naught is a maximal element. If you tell me that somebody in some element X is better than or greater than X naught, okay, well, what do I mean by this greater than or equal to X naught? We are not defined. This means if you tell me X naught is less than or equal to X, then that means X equal to X naught, right? This is a standard thing in partial order. Whenever X is less than or equal to Y, you also say Y is greater than or equal to X. But Y is greater than or equal to X is by definition X is less than or equal to Y. Okay. Okay. If you say somebody is better than X naught, then that fellow must be X naught himself, nobody else. Okay. That is, I do not accept anybody is above me. That is maximal. maximum fellow will say everybody is below me. Okay. Let us look at a concrete example. With that, we will stop. Okay. Let us look at x equal to r, rather s equal to r. Okay. Now, what is my x? In my x, I look at all power set of r. Okay. Minus r, the singleton r. Remember, power set consists of all subsets of r. Therefore, r is an element. You throw it out. You follow. If you want, you can look at x s equal to a b c d etc. also. Okay. But let us do that. Okay. If you want, if you are finding it difficult, I'll come to that. Okay. Now, what is the order relation? It's the standard order relation. Okay. Partial order is standard inclusion relation. Now you claim r minus any singleton, fix any, okay, a in r, and look at this set, call it capital A, then this is a maximal element of x. Why? So what does this mean? Does it say that you give me an element here, that means B is a subset of R and B is not equal to R, right? If B is an X, right? Does that mean B is less than equal to A? No. What does it say? It says something else. If it's a maximal element, if you tell me there is a B, so is subset of R and B is not equal to R, and if you also tell me that A is less than equal to B, then A must be equal to B. This is what I want to prove. Is that clear? And let's go back to the definition. When do I say x naught is a maximal element? Give me any. Suppose you tell me there is an x, so that x naught is less than equal to x, then x must be x naught. If somebody is bigger than x naught, then he must be x naught himself. Okay. You follow that? Okay. This is what I have to prove. But that is obvious. Why? So if A is less than equal to B, what does it mean? This happens if only A is a subset of B. Right? Now I want to say A equal to B. Suppose A is not equal to B. What does that mean? Suppose A is not equal to B. This means there is at least one element, call it X, in B, so that X is not in A. Right? Yeah. But where is A? What is A? A is all of R minus singleton A. Right? And where now X is an element of B, therefore X is also is an element of R, because B is a subset of R. Therefore, there is an element X in R which is not in R minus A. There is only one possible element, namely that X must be equal to A. If X is equal to A, you understand that? That means X must be equal to A. If X is equal to A, what does it mean? B is A minus singleton A, which is R. But that's a contradiction because B is not equal to R, because B is a subset of X. X is all proper subsets of R. You follow that? Take your time. Do not be in a hurry. You follow that? And how many maximal elements we have produced? If I take any real number A, look at this complement of the singleton. Okay, take R, miss one point, then all subsets are maximal elements. So how many maximal elements we have found in R, in X? Uncountably many. As many elements as in R. You follow that? Therefore, there exists infinitely many maximal elements. But can it have a maximum? Okay. I claim it is not. Why? Let us look at my element A0. Okay. This is R minus 0. Right? Okay. Now suppose you give me yes, B in X is a maximum of X. That means what? A naught must be contained in B. not must be less than or equal to b. Do you understand that? It's a maximum, therefore every element must be contained. But just now we proved if a naught is less than or equal to b, that means a naught equal to b. You follow that? Are you sure? Yeah? Because a naught is a maximal element, therefore a naught must be equal to b. Right? What is a contradiction? There is a contradiction. Now let us look at a1 equal to r minus singleton 1. Right? Now for the same reason, what will I conclude? A1 is a maximal element, and since b is a maximum, a1 must be a subset of b. That means a1 equal to b. But that cannot be. The a1 also must be equal to b. Right? But that's wrong. Why? Because 1 belong to this. Sorry, 1 belong to a naught, but whereas 1 does not belong to a. You understand that? This will imply a equal to a naught equal to a1, but 1 is here, but 1 is not here. And 0 is not here, but 0 is here. So this contradiction shows x does not have a maximum, but it has uncountably many maximal elements. And let's go back to this example. Now you can see, okay, in this set, okay, with this I will stop. In this set, how many elements are there? These are the elements 1, 2, 3, 4, 5, 6, 7, 8, 9. I hope this is correct. Okay. Now there are maximal elements which are not maximum. Do you see that? There should also be 2 cube. Yeah. Can you think of maximal elements in X? What do I want? I am looking for. Let me draw a picture. It may help you to understand. Okay. I have 2, 3. And who sits above this? 2 squared sits above this. 2, 3 sits above this. And 3 squared sits above this. Do you notice that? Okay. This means, okay, 2 is less than equal to 2 squared, 2 is less than equal to 2 times 3, and 3 is less than equal to 2 times 3. This, you understand? Now here 2 cubed sits above this, and here 2 squared 3 sits above this, and he also sits above this, and here 2 3 squared he sits above this, and 3 squared he sits above. Am I right? Yeah. Okay. Now what are the other elements available? Let me see. Have I missed anything? Yeah, there is a 2 cubed and 3 cubed. That's it. 2 squared, 2 squared 3, 2 3 squared, and 3 cubed. That's what I thought. I'm making a mistake. 3 cubed. Okay. Now you can see that this is a totally ordered chain. This is 2 2 squared 2 cubed, or 2 2 squared 2 cubed. This is a chain, or 2 2 2 times 3 2 times 3 squared. This is totally ordered chain, or 3 2 3 2 squared 3. This is a chain. Do you understand? There are many chains. Okay. Okay. Next, notice that this is a maximal element because there is nobody who is above him. You understand? So all these elements are maximal elements, right? But there is no maximum. You understood this? So these are the maximal elements and no maximum. And similarly, I have not defined, these are the minimal elements, and there is no minimum. Okay. Just as a parting cake, if you look at any field, for example, all of you are always fond of film industry, right? Look at your film industry. Okay. Let us look at Tamil. Okay. Then there are a lot of good actors. Rajinikanth, Kamal Hassan, Surya, Vikram. There may be many more. Okay. Just whoever Dhanush, whoever came to my mind, I'm saying. Now there is nothing like the best actor. Every actor is a maximal. That is, you cannot say in this particular thing he's better than. There is somebody who is better than this guy. Okay. In some aspects, somebody may be better, but not in everything. Similarly, look at the Hindi, same thing. Similarly, take sports. Let's take tennis. Then there will be some top three or four players. They're all maximal players, maximal elements in that order. You cannot say somebody is the best. Okay, he is good. He is also good. He is also good. Uh, so the point I am trying to say is many people believe the maximal elements are mathematicians' concoction. They just like that imagine some weird things. No, it's a real life, right? You may have two good friends, you may not be able to compare. Both are your best friends. There is nothing like the best friend, perhaps. Both are your great friends. So you may want to say both are best friends, but you cannot compare. You cannot use the best, right? As per English language, but you will still say that. Okay. Please go through, take your time. I had given some good examples. Okay. We will come back with some more examples and end up with John's lemma in the next lecture. Okay. Spend some time because, as I said, many times people very quickly go through. That is why they have a problem with partial order and John's lemma. Go through this example, understand the difference between maximal element and maximum, and similarly minimum and minimal element. I have not defined, but you should check your understanding using how to define minimal element, how to define minimum, and give examples of a set which has a minimal element that but not a minimum. I already had given. If you are alert, you would have noticed it. Okay. Thank you very much. We'll meet again.